Thank you very much for the introduction, Georg. Thank you very much for the invitation. Also, I had a chance to look at Dermo. It's astonishing to see it there. I was just surprised because I made my diploma thesis on the Dermo with a computational fluid dynamics parallelization. At that time, you could get a diploma with a parallelization. Times are changing. Okay, good. So today I would like to report about what's going on with machine learning and weather prediction. So at first, a little bit of historical review. Then I would like to give you an introduction into how weather prediction is done in general, what the components are algorithmically, what data they use, and all these things. And then we have a look about the integration of machine learning that started, let's say, with the first attempts in 2018-19, but then there were some quite astonishing papers in the year 23, and since then it accelerates. And of course, Google is involved in that, Google DeepMind. We will have a look at this GraphCast as one of the representatives of machine learning-based weather prediction concepts. And then we have a look at the ECMWF. The ECMWF is the Center for Medium-Range Weather Forecast that we have, Reading-based in the past, now moved to Bologna and Bonn. And finally, I go back to something that is not yet machine learning-based. That is the icon model that is used by DWD, because I would like to show you one of the visualizations that the Max Planck colleagues did a few years ago. So, of course, history of weather prediction. Obviously, we do this for millennia. Yeah, we always want to know what will be the weather for the next time. So for the crop and all these things. And in the end, we would like to know what is the atmosphere, let's say temperature, precipitation, things like that at a given point of time, at a given location. And in the past, all that was done qualitatively. People made observations, then they had some special kind of calendar, and it started to become formalized in the late 19th century. Then they had the first attempts of putting together the formulas for that, and then they started to do a little bit of hand computation. What you need is, of course, then quantitative data about the state of the atmosphere, if you want to make it in your area. If you want to make a global weather prediction, then, of course, you also need to know the state of the ocean. So meteorology as a science developed, and then we had the first weather report in 1st of August, 1861. That was in England. I always think that weather prediction as a topic is more for those countries where the weather is notoriously bad, yeah, because I think could not have developed in Spain or so. Nobody's interested because you say, okay, tomorrow the weather will be the same as today, it will be sunny, and in a week later it will also be sunny. Just here, and also Hamburg is very, let's say, have a strong scientific field in that. Weather maps followed a little bit later, and then also they started with transferring the weather prediction via telegraph. So they developed the formulas for that, and one of the fathers of meteorology is Bjerknes. And Bjerknes put together an early set of formulas, partial differential equations that could be solved at the time, but of course only by humans then doing the calculation by hand. And Bjerknes said that there should be a way to predict the weather out of given conditions at a certain point of time, and the formulas for then a certain delta t, but he couldn't show a practical way for that. And Richardson, 20 years younger than Bjerknes, developed a concept for that. The concept was published in a book that is called Weather Prediction by Numerical Process, a pretty famous book in this field of meteorology, because of Richardson developed a concept of how to do a weather prediction by calculation. Yeah? So this is my famous citation from the book. Richardson says, perhaps someday in the dim future, it will be possible to advance computations faster than the weather advances, and at a cost less than the saving to mankind due to the information gain. The citation is important for several points. First, dim future. This is us. Yeah, I mean, it started a bit earlier, but basically it's us. Then this point of doing it faster, because you want to predict something. Yeah, you would like to finish your computation before the weather arrives, which was not the case in the old times, because it is said that Richardson did a hand calculation for 2 data points for a prediction where what a certain state of atmosphere should be in 6 hours, but it took him 6 weeks to do that hand calculation for that. So the speed is, of course, an issue. By the way, in meteorology, they do this forecast. We are interested in forecasts. But to find out whether theory is correct or not, they also do these things called hindcast. That means hindcast is a forecast in the past. So sometimes it's important to know, okay, how did it develop, let's say, from an ice age to the year 2000 or something like that, where most of the part is then bringing it from an ancient time to a more recent time. And then the time it takes you to do the computation is not so important, of course. Interesting is that Richardson already mentioned the costs. So he said, and also the benefits. He said there will be a benefit for society. There will be savings by having these predictions, and there will be costs for doing that. And at some point of time, we will have less costs than we have benefits. And I will show you later how that fits together. Interesting. If you look up weather forecasting in Wikipedia, then they speak about weather forecasting in the United States, and they say that in 2009, that is here from Wikipedia, the US spent approximately $6 billion for weather prediction forecasting and all these things, producing benefits estimated at 6 times as much. Because it's for, let's say, for the ships, for the vessels, tornado warnings, all these things, evacuations, when you should start with harvesting, all these societal aspects that are connected to having a precise weather prediction. These are benefits for society that you could try to quantify, and they do that, and then you end up with an amount of money, and then you compare it to the effort, to the money that you spend for the weather prediction, and that what you gain is much more. Interesting fact, by the way, because the main actor in the United States is NOAA, the Center for the Atmospheric Research and all these things. They are confronted with a reduction in budget that will force them to hire between 10 and 20% of their staff. And that means that in future, they will not be able to have the same quality of prediction, of course. And that will harm the benefit side as well. So Richardson said, okay, it takes me a certain time to do the computation. So how many people do I need? Because we have the year 1920, no electronic computers, of course. And Richardson developed a concept, and that is written down in his book, where he said, we need something like 64,000 humans to have a global weather prediction with grid spacing such that you have 2,000 grid cells. He estimated that with 32 people per grid cell, you can do this prediction where you say you predict it for a few hours in advance, and it takes you half the time to do all these hand calculations. And he set up a concept of doing that. And basically, by the way, this is something like message passing in the end, because this is a drawing from the early 20th century about Richardson's so-called forecast factory. You see here a sphere-shaped computer room with the balconies, and on each balcony here you have 32 humans doing the computation. They put it into this tube, written on paper, of course, put it on the tube, and then you have a pole in the middle, and you have this pneumatic transfer of the tubes to the organizers, to the, let's say, operators in the middle of the pole. The operators have torches, and they have red and blue light to indicate to the people on the balconies whether they are too fast or too slow. So they do the load balancing by this, and they do the transferring of the intermediate calculations of all these grid cells in the end on the balconies to the people on the pole, on top of the pole, and they assemble then the weather prediction. Everything is described in the book in complete detail, how that should be organized. And it's interesting because it's in the end parallel computation at its best, just with humans. Then, of course, finally, we have something like an electronic computer. And the first weather prediction was done in 1950 on an ENIAC. The Americans always think that ENIAC is the first computer. Well, we know better. They did this here. One of the first applications was then weather prediction under the control of Charney, a scientist, but also pushed forward by John von Neumann, for example. It's quite interesting. And they did weather prediction, but on very small grids. So they had something like, I don't know exactly, maybe a dozen by a dozen grid points or so, and did it for the US. So the spacing was more in the range of maybe 500 kilometers between the points. Took them 24 hours to produce a prediction for the next 24 hours. But the literature says that most of the 24 hours was spent by hand-organized preparation, pre-processing and post-processing, so to say. And the ENIAC part was only a small part in the middle. Then time advances up to more or less now when we start with the machine learning that I would like to present here. And of course, we have better computers since 1950, and we have more investment. And very interesting is if we at DKRZ, we compare how much money our, let's say, partner centers have. And if we look at the Met Office in UK, I mean, they do operational weather prediction. DKRZ does not. We do climate only. They do operational weather prediction plus some climate research. And in 2020, they made a procurement and ended up with a deal with Microsoft for 2 generations of computers being installed and operated for Met Office. The total costs are in a range of 1.4 billion euro for 10 years. And the interesting point about that is that, and it's the second time already for Met Office, that they conducted a study before that and tried to estimate the benefits for society. And with adding up all the numbers, unfortunately, this thing is secret. Yeah, that's handed over to some politicians. Nobody has ever seen it really. But the document says that the financial benefits for society, GB-based society, will be in the range of 13 billion, and thus an investment of 1.4 billion is more than justified, of course, if the numbers are true. It's already the second time that they did that, and it would be interesting to see it because, let's say, in the beginning of the 2010s, I had several workshops at supercomputing with the title Cost-Benefit Considerations for HPC. And that is interesting how they put together the numbers here. Unfortunately, it is not publicly available. It advances with the computers. We have global forecasts, global climate models, we have higher resolution, we have cyclone models, ocean models, and then also we have these ensemble forecasts. The ensemble means that, because usually you have an initial state of from where you start to do the prediction, and you get one result. And to check for uncertainties and for mathematical stability of these models, what you do is that you have several dozens of slightly changed input, where the input is slightly changed starting states, let's say up to 50. If your compute time allows that, then you have 50 ensemble members, you compute 50 times what the resulting weather or climate situation will be, and then you do a statistical analysis over these 50 ensemble members, and you do selection and statistics and things like that to have a higher degree of quality of your result. Then, of course, that multiplies the necessary compute time by a certain factor. Could be up to 50 then here. Improvements over time are significant. So Roland Potthast, a colleague of mine from the German Weather Service, DWD, gave me that slide here. So what we can see here is certain lines where we have an x-axis, which are the years, and several generations of weather prediction models that they operated. And the y-axis gives you a certain quality measure for the quality of the prediction, not starting here with 0, instead with 0.6 already. And you see that depending on for how long the prediction is, that is called the so-called lead time. So we have lead times between 1 day and 7 days. That is for air pressure prediction. Then you see that over time, quality is getting better and better. The latest model that they operate, and I will report about that a little bit later, is the ICON model. So there is always improvement, and this is a chart that covers then a lead time up to 7 days. But usually for weather prediction, you would like to go to 2 weeks. After 2 weeks, then a certain barrier, which makes it complicated.
What happened in the early 90s? With a sudden surge?
In the early 90s, a change in model here.
Different model. Okay.
It's a different model, a certain improvement. So the one is, I don't know what the abbreviation stands for. This is this BF something, and the other is this GM. So they have a completely different thing at start here.
Same at 2015, right, when ICON was.
Yeah, and with ICON too, exactly. So Peter Bauer, one of the leading guys of the ECMWF with respect to the computing aspects, gave a talk at the ISC in 2019. And in 2019, they were really still skeptical. So he said that while artificial intelligence methods cannot overcome the main bottlenecks of efficient computing, they can help alleviate algorithmic cost and support information extraction from both observational and simulated data. That strongly underestimated what machine learning will really be able to do and what what happened just in the following years after Peter gave that talk here. And I will report about that. So let's have a look at forecasting, how that works in general. So forecasting 101, so to say. We have the timeline here. That means the timeline tells us for how long we would like to make a forecast. Yeah? So you have something that the meteorologists call nowcasting, that is between minutes and hours. That is if you have let's say a strong rain event, a flooding or something, where they want to know where it will spread, who will be endangered, things like that. Then we have the so-called medium range weather forecasting. This is what ECMWF is specialized at. That is already on the global range. That is between single days and usually 2 weeks of duration. And then we have longer term predictions that already go also into climate predictions. So we have starting at the 2-week barrier, more or less, individual months, which is called subseasonal forecasting, and then go to seasonal forecasting and climate forecasting. What mathematics do we use? For the nowcasting, everything is pretty much deterministic and depends more or less on the atmosphere. So you don't have to consider what's going on the ocean, unless you have a tsunami that you would like to compute or something like that. Now, for medium range, it will be a global thing, differential equations tending to be no longer really deterministic, has to integrate the ocean already, and then you have the stochastic models for the longer periods where you have ocean-driven dynamics. The point is, if you compare atmosphere and ocean, and you compare the times it takes until, let's say, everything is turned around one time, everything is like in a whirl turned around one time, then this is in the range of single weeks in the atmosphere, but it's in the range of hundreds of years in the ocean. So the ocean moves extremely slowly. That means that for the global models, everything that happens in the ocean is very important for what then will also happen on land, because there's an exchange between heat between ocean and atmosphere. So understanding the ocean for the longer term models is indispensable. This is where we see the machine learning based success stories. And this is what I will report about in the next slides. This is what ECMWF, for example, is concentrating on. And this is what the users at DKRZ are concentrating on. So at DKRZ, computations that are done at DKRZ are mainly for climate simulations. So it starts with seasonal, decadal, going then for centuries and sometimes even longer if they want to simulate some ice ages. There are also machine learning based success stories, but they are pretty different. I will give you a short overview over that in one of the later slides. So how to do the forecasting? When you do the forecasting, then usually you start with a situation that is known, which is a combination of something predicted plus something that is obtained by sensors. And then you do a forecasting step for a delta t. This uses these equations, parallel differential equations, and you do a forecasting step, and that is computational, extremely intensive. So you do one forecasting step, you end up with a t plus delta t, then you have the next situation, you do a forecast what will be the situation in 3 hours, for example, and then you do a post-processing of the data. That means you put together the weather reports that are delivered to the people, and at the same time, or let's say in parallel to that, what you do is you do a so-called data assimilation. So you have millions up to billions maybe during a day of sensor data information. And the sensor information that is not, of course, equidistantly spread over the world, because you get information from ships, from land sensors, from balloons, whatever. The sensor information has to be merged into the result of the prediction, such to have a consistent picture that fits together with the measured data and with the predicted data. And that is done with a step that is called data assimilation. So the assimilation merges the observational data into the predicted plus former observational data. This is also HPC heavy. They use Kalman filters in certain variations for that. A very complicated thing for each assimilation step. You have dozens of millions of individual data information that get integrated into your already available predictional data. So you end up with that is the one in the middle, you end up with a new start situation for your next forecast step. And then you continue with this chain of process steps that you have here. And the important point to know is now that the ML-based success stories the ones that are available in literature, they just cover that forecasting part. They don't cover this assimilation part. And DWD told me that they are computationally more or less equal. Assimilation is a little bit lighter than the prediction, but it's also HPC heavy. The point is that politicians approached DWD and said, now, as there has this machine learning progress, you don't need the big computers anymore. And currently the answer still is, you are wrong, but it changes. It's important to know that just only this forecasting step is covered by what I will report about in the next slides. Yeah? Data assimilation has still to be handled, and the progress there is slow, but there is some progress. So the integration of the machine learning into the forecasting. DWD started with first efforts in 2018, also ECMWF. And then there's a quick adoption of machine learning methods, but you have to know that DWD, ECMWF, they have so-called products, which is the weather prediction that goes. DWD, for example, is responsible for the German air traffic, and that needs a certain degree of reliability. So they do not easily switch from a production mode that uses partial differential equations to a production mode that uses machine learning, obviously. Yeah, but it will change in future. So then in the year 2023, we see three exceptional results being published about how to base weather prediction onto machine learning. And the three results are by NVIDIA. There's a product called ForecastNet, or let's say an algorithm, a program called ForecastNet. Then there's Pangu by Huawei, and then there's GraphCast by DeepMind. Published during the year of 23 and setting new marks for what can be achieved when you integrate machine learning into weather prediction. So what is now the success story behind it? Why is it now coming in 2023 just to that point? The reason is that machine learning is very advanced at that point of time. So the algorithms that are used for Forecast, Pangu, and GraphCast are all from that area that is now rapidly developing. Forecast and Pangu are transformer-based, and GraphCast is a graph neural network. And I mean, that is put on graphic cards. Everything is accelerated heavily, and that helps a lot. But the question also is, where do they get the training data from? And the training data is obtained in mostly, for all three of them, in this case, definitely, is obtained from ECMWF, from a data set that is called ERA. And I will speak about that in a moment. So algorithms and data are the foundations now for the success of these three algorithms. And of course, then DWD and ECMWF developed their own algorithms too. So the ERA data, that is very important. That is the training data for the neural networks for all three of these publications. The ERA data set at the ECMWF is put together from data that starts in 1979 up to the present time and comes from all the observational data that they collected during these times. And then what you do is you have the observational data that comes from all types of sensors. Let's say this is aircraft, ships, balloons, buoys, whatever. Measurement stations on land in the cities. The Americans had, for example, at each embassy and consulate, they had their own measurement station, which they also will shut down now. Will have a very negative effect onto weather prediction issues in the individual countries, usually underdeveloped countries, where they relied on that. Will be switched off. Anyway, that is terrible. So, and the ERA data set is now harmonized to a grid of, let's say, more or less a virtual grid space of 31 kilometer and with a 1 hour interval. Of course, the data that you have, the measurement data, is not necessarily on the grid points. It's not necessarily within these 1 hour interval. Now, this is again achieved by using these filtering and computational concepts that they also use for data assimilation. In the end, this so-called reanalysis is something like a post-processing of data, where the data analysis, the data assimilation that I showed you a few slides before is just a real-time process during the computation of a weather prediction. So this year, the reanalysis is computational heavy load, takes a long time, and ECMWF has this harmonized set of data. And this data set is now then used for training of the networks. And the interesting point that we will see also a little bit later is that it is on this virtual grid size of 31 kilometers. Nevertheless, they are, even with this data set, able to predict small scale effects like tornado trajectories, for example, things like that, that are smaller than the 31 kilometer grid size. still it's not 100% clear why this is possible. The data set, let's say, compared to what we save, not that big. It's 1.5 petabytes. So you can also download it at DKRZ or from ECMWF. So this is what was used for training for these three algorithms that I presented. Now we will concentrate on GraphCast as one of the representatives because that is the most, let's say, advanced one also. And they used something like 36 million parameters in this graph network. By the way, just to say that the ERA data set has, of course, things like temperature, humidity, wind, and all these things. Yeah, so you could easily, even if you're not in that field as a meteorologist, you can easily think of, let's say, 1 dozen of variables that come to your mind. But the overall set size in the database is in the range of 7,000 parameters. Not for all 7,000 parameters, they have this from 71 or 76 to something. But they have something like, for example, vegetation that you have on a certain point on the surface, on the global surface of the Earth, or where you have sand, for example, things like that. All that is in the ERA dataset. Unfortunately, this is a very thick paper, by the way, the GraphCast thing. 150 pages or so with appendix. Unfortunately, I did not find which essential parameters they used, the variables for the metrology. I would assume just the basic ones. I think of maybe 10 or so, which should be sufficient to have a decent weather prediction. And they had a small network, trained that. It took them 4 weeks on a very small cluster with TPU devices. And then for making the forecast, those does then go very quick. They just do it on a PC. Now the forecast step on a PC lasts between minutes and hours. It's just nothing. You don't need HPC for that. And now in the next step, we will compare that to what happened at the ECMWF and how that relates to it. So result number one, this is from the summary more qualitatively. They have so-called targets. Target is always a situation where you have a certain variable like temperature or humidity for a certain area on global space and for a certain period of time. So GraphCast, as you see here, outperformed HRES. HRES is this high resolution model that ECMWF is applying currently. They're also switching to AI now. Performs at most of the targets this HRES significant and 90% outperforms it and significantly outperforms it for 89%. Of course, the statistics behind what the measurement criteria is can be found in the paper then. I will not go into the details here. Also, the GraphCast outperformed the other ones, in particular the Pangu. Pangu is a very good one. They compared Pangu to GraphCast, and you see that GraphCast is better. The paper that you can download has 132 pages, only just these comparisons. Yeah, it's just that they say, okay, we compare something like temperature, density, precipitation or so for certain areas. We compare then GraphCast to ECMWF. And I will show you two examples of that. One is comparison. It's always a comparison between what ECMWF is doing with the HRES model that they have, that is not ML based, and the GraphCast. And for example, what you see here is an example for cyclone tracking. Cyclone tracking is, they always thought it would be more complicated because this is a very singular event. They thought, okay, let's see what the network can tell us, because they are not of the number of events being present in the ERA dataset is not that high, of course. Yeah? Because also in the past, there were not so many cyclones as they see now in more recent times. Nevertheless, if we look at the track error of where the cyclone moves, and then we look at GraphCast, that is the blue line here, plus the variances that might apply for lead times of 0 up to 5 days, then you can see that GraphCast is more precise than the HRES predictions were. The same holds for something that is called atmospheric river. Atmospheric river is something that is very important in meteorology. These are streams of humidity where the stream is something like 500 kilometers wide and up to several thousand kilometers long. And these streams, they are in let's say an elevation of something like 2 kilometers or so. They are major components to transport humidity between different areas of the world. And they are very important as an influencing factor for the weather prediction. So it's important to be able to predict these atmospheric rivers, just like normal rivers, you just can't see it. Yeah? It's important to predict them as good as possible. And again, we see that here they have this root mean square error in kilogram per meters per second, just that moving humidity there. They compare what GraphCast is predicting and what HRES is predicting, and GraphCast is better here. And then you can go through hundreds of these comparisons, and you will mostly find that GraphCast is better than HRES. And of course, it's much, 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 much faster. Yeah, that's the important thing here. That was all the discussion in 2024. So I gave that talk for the first time in spring 2024. I put together the data. But since this time, everything accelerated. Yeah, so I always have to check the literature again. So what's new now? At that time, there was a discussion. Can these ML things predict something, some events that are in a smaller grid space than the 31 kilometers? Yes, it can. So the scientists don't really know why this is the case, but the predictiveness, the predictive quality is pretty high. Can it predict seldom events? Also, this holds, and it's not finally clear why this being trained on ERA 5 gives that good quality. So scientists are still discussing that, and you can learn about these discussions everywhere when you go to conferences. I will show you in a minute. The interesting question is, what will be the influence onto the scientists and onto, let's say, the people who buy computers, and for the politicians who have to pay for the computers? Yeah, politicians already said, it's okay, you do the training on a TPU cluster, and then you get a small computer for doing this prediction step. You don't need that much of computational performance. And for the scientists, there is, of course, the challenge that they are now confronted with the concept that constantly, starting from, let's say, these publications in 2023, constantly gives better results for weather prediction in a range of up to 2 weeks than the partial differential equation-based systems give us. Yeah? And for a fraction of the energy consumption and for a fraction of the computational power. So they have somehow learned how to deal with this. And obviously now they develop their own machine learning approaches. Peter Düben, one of the leading guys in that special field here at ECMWF, gave a nice talk at the supercomputing conference. And I just give you the headlines of the slides together with the answers. All the data that is behind it, the proofs for all that are on this slide set. Slide set is, I think it's publicly available. Or Peter will send it to you if you're interested in that. So for example, questions are, can machine learning models avoid the smearing out for long predictions? That means going from 1 week to 2 weeks and maybe a little bit more. The answer is yes. Can machine learning models learn uncertainties? That is also important because they want to work with these ensembles. And then the uncertainty quantification is an issue. Seems that machine learning can support that. Can it represent extreme event? There's a clear answer, yes. Also, nobody, in my opinion, at least I didn't hear anybody speaking about it. I think they don't know why, but it just works. Can it represent physical consistency, like conservation of mass, energy, momentum, things like that? The answer is yes. And finally, and Peter has several slides on that, but that is, let's say, slides from a meteorologist, which I do not fully understand. The question was, will we be able to do data assimilation with machine learning in future? And seems to be that, yes, they do have some success with this already. And that means, of course, that also this heavy load data assimilation process that currently needs heavy HPC could perhaps be reduced to something that works on smaller computational systems then. So there's a lot of movement in that field. The next question is, of course, will machine learning support climate simulations? We are not yet there. I will show you some details about that. So I found out that now, if you look at a paper from that area, you just have to check the date, because it changes from month to month. What was the fact in spring 24, when I gave a first version of that talk for the first time, changed already until I had a second edition of the talk in December 24. There was quite some movement in that field. And in particular, they had this publication of GenCast, which is another product from Google DeepMind. That is a prediction system that is able to predict up to 15 days, so 2 weeks. Then also runs on a small computer, just a 5th generation TPU from Google. Google, the prediction takes only a few minutes. It's just nothing. Energy consumption in the end is, you can neglect it. And that, of course, there are no meteorological institutions behind what Google is doing here, but they plan to integrate that on other places. And ECMWF is also developing its own system that is called Artificial Intelligence Forecasting System, AIFS, a new operational model that is also able to do this data assimilation. Data assimilation is currently here not ML supported, but could perhaps be in future. And also it's not yet for ensemble members. They target for up to 50 ensemble members. And then that was a little bit strange because there was a publication in Heise-Ticker by end of February where the headline was, but I cannot find that in the press release of ECMWF. The headline was that it will only use a fraction of 1,000 of the energy consumption for doing that prognostic step, the prediction step, with the AIFS compared to the HRES that they had before. So there's a considerable reduction in energy consumption, of course. And that frees energy for other scientific issues that they might want to push forward where they do not have machine learning. Just one point about what we do at DKRZ. You cannot easily transfer the concepts with this era data you cannot easily transfer that to climate. Instead here with climate, we do different things. I mean, we are not a research institution. We have a small department for machine learning and data analysis headed by Christopher Caro, and Christopher has certain projects for that. So one project that uses ML, and by the way, in this one uses ERA, in fact, is infilling of missing data, weather data in historic data sets. So you have historic data sets from ships or whatever, from also 19th century with lots of gaps. And astonishingly, you can fill that in a qualitatively high way by using machine learning methods. What else is he doing? He now integrated climate simulation result data into large language models and allows the scientist, the meteorologist, or the climate researcher to conduct research by doing a conversation with this enhanced ChatGPT thing. Up to a point where the people complained and said that he would endanger their positions. Yeah, so they might be workless in a while if this moves forward. So that is very interesting how to do that. I mean, I guess you all use ChatGPT for doing something with it, also some scientific aspects. And now if you train or if you hand over relevant data from climate simulation results to ChatGPT, then you can ask certain questions and conduct research by a conversation. These are things that we are pushing forward at DKRZ in the field of machine learning that is integrated into climatology. A short announcement just because it fits here our topic, and I think I will attend that. The colleagues from Zurich, from the Swiss National Supercomputer Center, and from the ETH, the colleagues who we collaborate with in this development of ICON. They announced the workshop for beginning of June, where I very much like these two sessions, B and C, harnessing the power of AI in modeling weather and climate, harnessing the power of physics-based modeling, and then session D, bringing it all together. It will be a 3-day workshop. Peter Düben will also be there, all the leading people who push forward machine learning, weather and climate in Europe. I think I'm neither a meteorologist nor a machine learning guy. I'm an HPC guy. I'm the head of DKRZ, just observing all that and thinking, okay, that's really cool what's going on. So I think I will attend that workshop to learn more about the details. So finally, just because it's so pretty and you will see it just in a moment, I will go back to one example from ICON. ICON is the model that is developed between the German Weather Service, Max Planck Institute for Meteorology. They are in the neighboring building to DKRZ. Then also DKRZ is involved in that, and the KIT and the Swiss people. And with ICON, ICON is used for climate and for weather because, of course, the physics inside is, of course, the same. Yeah? So what the people at MPIM did was the following. There is a famous photography from the Earth that is called the Blue Marble photo. That was taken on December the 7th in 1972 from Apollo 17, the last crewed lunar mission. And for celebration of 50 years anniversary of that picture, the Max Planck people decided that they will recompute that meteorological situation that is visible on the picture. So what they did is that they said, okay, we take the ICON model, because the ICON model, and that is what they are proud about, or what they are proud of, is the ICON model is a cloud resolving model also for precipitation. precipitation. In particular, it's cloud resolving for a small scale, like 1 kilometer scale for the clouds. And it's the first representative that we have available. Of course, it needs a lot of computational power. It's not yet based on machine learning. It's just based on plain HPC. So they decided to simulate the weather of this particular day, December the 7th, 1972, together with a project together that we pushed forward, Max Planck with NVIDIA and DKRZ. And they did a 2-day simulation of the weather development. So they started 2 days before the photography shows us what's going on. Ocean simulation, because the ocean is always that slow and important, started 4 years earlier. And they did a reanalysis data from what was the case on the 5th of December in 1972, just 2 hours ahead of when the picture was taken. And then they computed that on our computer on Levante. It took them 7,200 node hours per simulated day. And they simulated 2 days, so 14,000 node hours on Levante. And that shows the animation. Of course, it moves very slowly, but we see here, this is, here's Africa, Madagascar. We see here clouds shifting away during these 2 days. Let me see. Okay. During 2 days, of course, there's not so much movement, but there is, because sometimes people said, maybe that was more static. No, it's not static, but the movement is not that big. And then finally, if you compare what the picture showed us, that is this here, that is the picture on the left side, and what was recomputed with this cloud resolving precipitation able icon model, then you see that this looks very, very similar. For the people from Max Planck, of course, a proof of concept for what the model is able to do. This one is still based on regular physics. Everything is HPC heavy. That will also deploy machine learning concepts in the future. And with this, I would like to finish my talk. Thanks for your attention. There will be some references then for you later. You can have the slides.
Yeah, one question. These machine learning models that seem to outperform the classical weather prediction models, they need to be retrained at some stage, right?
Yes.
Do you know how often they are being retrained? I mean, if that is an ongoing effort.
Right. Currently, this is only proof of concept. They do retraining, and the point is that ECMWF adds these new data with new reanalysis to the end of their file, so to say, and then you can download and retrain. So they give us the date, which data they used, and I think to remember that they said that they used data up to 2022 or so for the first part that they used for the publication in 23. Obviously, they will, if this goes into an operational mode, they would be wanting to get hold of every data that ECMWF is publishing, because the more recent data will have this more seldom extreme events, because the frequency of the extreme events will be higher with more recent parts of the data. And the data is accessible, so they can just download that and do a retraining with adding that one to the existing data set. And as the training, by the way, is not that compute intensive, I'm pretty convinced they do it.
There's a question in the chat. The open source icon code has roughly 800K lines of Fortran and 200K lines of C. Is there a strategy how to maintain such an application when Fortran is not as commonly taught anymore?
Yes, there is. So there's for something like 4 years, I would say, we have this consortium where we have the board of directors who supervise what's going on, do more the political decisions. I'm involved in that. And then we have a board of so-called coordinators from each of the institutions, and they take care of pushing forward the software engineering process. And the plan is to bring, by the time, these things more or less to C++. And then also you have to see that Fortran was in the end never really taught. So they had to learn it on their own. And that's a burden, of course, but it has to be modernized. And there is a certain process going on with this. It has been in the last 2 years not on the top priority because we were busy with some other things. The other things were in particular preparing the icon code to be available as open source, and then also as open contributions. So we set up all the processes for doing that. And that means all the legal issues with making that, let's say the history in Git and all these, the author history. There were so many legal questions such that, let's say, the refurbishing of the code, bringing it to a new program paradigm, lags behind a little bit. There are some parts inside Icon that are already adapted to GPU, for example. That was done a few years ago together with the Swiss colleagues. But it's, for example, not true for the part that runs on the DWD. Yeah, they have it on their NEC machine. Yeah, that's a very complicated thing. We do our best to get it somehow more advanced.
When looking at slide 10, I think where you showed like the different forecasts for 1 day, 2 day, and so on.
Mhm.
In the end, like 2024, 2025, you could see you had a correlation of still, what is it, 0.8 for 7 days.
For 7 days, yeah.
Does this mean that in 80% of the cases, the prediction is correct? What does it mean?
That is a question that I will not answer because I don't know the answer correctly, but there are many jokes about that because the joke is, for example, will 8 out of 10 meteorologists think it will be this and the 2 others will think the opposite? It's complicated. I think if you ask Roland Potthaus for what the quality measure really means and how this is mathematically computed, then you will have the answer for that. But sorry, I don't have it. It just lags behind a little bit. There's always this joke that, let's say, for our weather here, that if on one day you say the weather tomorrow will be just like today, you have already 70%. So the question comes up, how do you spend so much money for these computers just to get from 70 to 80 or something? Yeah, I don't know exactly what's mathematically behind it. Sorry for that. But there is a mathematics behind it.
Where does the deficiency of the traditional PDE-based forecasting come from? So if you compare the AI-based methods with the PDE-based methods, there's a clear gap in quality, obviously. So is the deficiency of the traditional methods based in a lack of the correct description of physics? Is it the discretization? Is the grid not fine enough? Are there other effects? So what is the reason would they cannot catch up? They don't give the same result.
Do you speak about this, what we saw with the Apollo picture or in general, or what?
The comparison, for example, with the atmospheric rivers, the deficiency or the inaccuracy of the PE-based methods in comparison.
I think it's just that the way to describe that is the mathematical way that would be exact, but in reality, there are too many disturbances coming from whatever sources. Now, just let's say if you speak about the rivers, then something is going on the ground that has an effect on the river, so the river deviates, but that is not represented by your formulas.
Okay, but
that is for the PDE. You say it again?
It is learned by the AI.
By the AI, it's learned, yeah. And I think that is the reason why the AI here is a little bit better. Because for the PDE for the PDE solution, you don't have these historical effects being represented. Yeah? What is in the era data, to some extent at least, and even this is a small extent, but it is there, which is not there if you make it correctly with PDE solving.
There's a follow-up question that also connects to the next question in the chat. To what extent do the ML models enable an understanding of weather processes? And also that's my question. Can we learn something to improve the traditional models from the way AI does it?
That is a good question. So I would say in general, the ML things are good for 2 things. One thing is you can do things much, much faster, and you might perhaps sacrifice a little bit of quality, but here we see that this is not even the case, and you have higher velocity, and you don't ask this question. Yeah. The next thing is you can do ML-based some science where you get new insights, but the ML will not explain it to you. So I think the next step, of course, because explainable AI, the people sometimes write that into their papers, yeah, but it does not exist in that field. I've never seen it. The explanation has to follow by real research that is conducted. My opinion about that was always that if you do it in weather prediction, and weather prediction is so successful with it, then that is understandable and it's okay, because you say, okay, weather prediction is wrong anyway. So if we do it with ML, even if it would be a bit worse with ML, which is not the case, but even if it would be a bit worse, you would say it's for a fraction of the energy consumption, and it's so fast, I need such a small computer, I do it via ML. But then you will not ask the question, why? Huh? And so my assumption always was that for the climate researchers, that they will never adopt ML in their research, because they are interested in truth. They want to understand, how does this develop? What are the governing laws behind it? What is then, how is everything connected? And I am still convinced that they will not be satisfied with a however successful climate prediction you might have being based on an ML that don't give you any explanation. And so the science will not stop. ML will just be an additional tool. And currently what we see is that they get, based on ML, interesting insights where they say, hey, I've never seen that before. What is the reason for it? But then they ask ML for it. Then they go back to their PDEs and try to find a way to reproduce that perhaps and understand why it is. ML at the moment will not give you any answers. It just gives you quick and good results. There is one more.
Okay, yeah, thanks a lot for the talk. So my question is from a meteorological perspective, and just, the background. I'm professor of climatology at this university, and we are running weather and climate models in our group. And one thing I noted when I read this AI literature is that many things are impressive very clearly, but nobody of these people talked about precipitation forecasting. I think so. As a meteorologist, precipitation is a super complex process. And even if you model it, you need a lot of background knowledge on atmospheric processes to understand the model output. So my question to you would be, do you know about any efforts to include precipitation in AI model forecasting, or is this still a little bit away?
I would be astonished if in the GraphCast appendix with all the comparisons of these targets and the things, I would be astonished if there's not a single one with precipitation. I wouldn't believe that. On the other hand, I know that, let's say, with the icon model in particular, it's just the thing that they can compute. It's not ML based, it's just PDE based. And that's an important thing. I remember that there was a discussion about whether these particular floodings that we had in Germany would have been able to predict with an ML, but I think there's not a clear opinion on that. If you maybe check this Google GraphCast paper and check, just for the word precipitation in the appendix, I am pretty sure that they have comparisons between the ECMWF model and what GraphCast is predicting. I would be astonished. I didn't make a vast selection of it, as you see. I just have the two things like atmospheric river and trajectory tracking.
Yeah, I just found it interesting that because I read their paper, which I think is only 4 pages in Science, and they don't talk about precipitation at all, but maybe it's somewhere in the huge appendix. Yeah.
Yeah, you should check that. It's 130 of comparison. I would really be astonished if there's nothing about precipitation, because as you say, that is an essential thing. British people, WF in particular.
Yeah, and I just wanted to add, I fully agree on what you just said before. On the other question, I think in their current state, ML models are not so helpful in teaching us more about processes. I think the PDE-based systems are still way ahead in that respect.
For example, maybe you ask Peter Dübmann for his slides, because there are many details with quantitative comparison with respect to the questions where I only gave the answers here in my talk. But Peter has a lot of material in his slide set, and that is for you, I think, really interesting to see that. Or send me an email and I can send you the slides or bring it together with Peter.
Yeah, thank you very much.
Last question from me. Talk about consistency. That's a very big topic with AI. We see it all the time with AI-generated movies, that people have different clothing at the end, at the beginning, for example. Mass conservation, for example, is a very big thing. Is consistency in these ML-based weather prediction models enforced by some external mechanism, or does it come out naturally? Does it just happen to be consistent?
As I understand Peter's slides, it just comes out of the data in a way that they really do not really understand. There's no enforcement for that. And considering that everything, let's say all these prominent examples here are all based on the ERA data, that is really astonishing.